Ladies and gentlemen, this is chapter 9.2. You should definitely read this part in the textbook. But we're going to continue on with what we talked about today in class, and that was using this table here. And we're going to use this table to predict what we call molecular geometries of molecules. Now, what we have here is right out of your book. It's table 9.2. And we can use it to predict what's going to happen in some bond angles and things like that. And so just as a review, we had bonding domains. So here are bonding domains. If you were a 2 and a 0 on bonding versus non-bonding, you would have a linear structure. And example is CO2. And this guy is going to have 180-degree bond angles. We talked about in class if you were a 3 and a 0, around that central atom right there, if you had 3 bonding domains and no non-bonding domains, you would be called a trigonal planar, and you would have 120-degree bond angles. And then we started getting into some things that compress bond angles. If you have an unshared pair of electrons, which are shown here, it's going to compress this bond angle down to less than 120 degrees, and that's what's going on there. So, and we talked about here in class, we have tetrahedrals with 9.5 degree bond angles, trigonal planar 107, and bench with 104.5 degrees. But what we're going to talk about now is, one, the effect of non-bonding electrons on multiple bonds, as well as those unshared pair of electrons and how they affect it. So slide down here. One thing was we have the example of a compound called phosgene, a really nasty chemical, which has a central carbon with a chlorine coming off and a chlorine, and then we have an oxygen. And we're going to go ahead and run the Lewis structure on this guy to make sure we have everything going on how we should. So for each chlorine, you're going to have 7 valence electrons, so it's a total of 14. Carbon's going to have 4, gives a total of 18. Oxygen's going to have 6 more, so we can see there we have 24 total valence electrons to deal with. 2, 4, 6 have been used. 8, 10, 12, 14, 16, 18, 20, 22, and 24. Now, the central carbon does not have an octet, so really what happens is we do form a double bond right here, just like that. Let me erase off those guys. And so that's what we get is our Lewis structure here. Now, this guy looks like, if you look at the central atom here on this carbon, it's basically got 3 and 0. And if we kind of scroll back up and we talk about a 3 and a 0, a 3 and a 0 is going to be a trigonal planar, nice 120-degree bond angle. It is a trigonal planar, but there's an exception to the bond angle. And the reason why there's an exception is that we have this double bond here, which is going to be a more electron dense location. And what it's going to do is it's going to put some pressure on those other bonds in this direction. It's going to put pressure in this direction. So what would normally be a 120-degree bond angle is actually going to be less than 120 degree over here, just due to that double bond. Now, previously we talked about, like in water, and you can kind of look up the screen here, water's right here. It has those 2 unshared pairs of electrons, which does compress the bond angle. Well, what we're saying now is you can also have double bonds compressing a bond angle as well. So let's keep that in mind. Okay, now I'm going to go ahead and erase some of this stuff because need to move it down. So I'm going to go like this. If you need to pause stuff to get it taken care of, that's fine. Now this is the next part of the table. This table is actually 9.3 in your textbook. You can look at it right there as well. And this is going to give us some more domains, bonding and non-bonding domains. You will need to know bonding domains versus non-bonding domains, and you'll need to know molecular geometries. So I should be able to give you an example, and you should just be able to go, okay, I can draw this. I know it's 5 and 0. It's going to be what we call a trigonal bipyramidal. So that'll come with time, a lot of practice. So looking at this first one here, we have PCl5. And just to draw this guy out real quickly here, PCl5, we have phosphorus and 5 chlorines. And it kind of looks something like that. phosphorus 5 chlorines, and if we do the Lewis structure based on the valence electrons, phosphorus is going to have 5 valence electrons. Each one of those chlorines is going to have 7 valence electrons. We have 5 of them, so it's going to give us 35. So we have 40 total valence electrons to deal with. 2, 4, 6, 8, 10 have already been used in the bonds, so we're going to go ahead and go around here. So 10 have been used. There's 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, and there we go. Now we've used up all 40. So in looking at our central atom here, we have a 5 and 0, 5 bonding and 0 non-bonding, and that's going to give us a trigonal bipyramidal. Now, it's kind of hard to see here. I'm going to kind of bring us back over and look right here. And if you think about these guys, some bond angles that are going on, we have 2 different axes going on here. From this B here all the way around like that, we can constitute what we call an equatorial axis. And these guys here and here would constitute an axial. Now, so the bond angles on our axial from here to here are going to be 180 degrees, just like maybe from this one all the way over to this one would be 180 degrees. And then on the equatorial would be the difference between this chlorine and this chlorine and that chlorine. It would be like an axis, the equator going around the Earth. Those would be 120 degrees each between the chlorines, if that makes sense. So we could talk about 2 separate sets of bond angles that are going on there. So there's a few other shapes. Of course, there's the seesaw shape going down here, one called a T shape. We have another linear that occurs in XEF5. And then we go down here and we have one called an octahedral, which is a 6 and 0, square pyramidal that occurs with a 5 and 1. And then we have a square planar that occurs at 4 and 2. So I'm going to give you a couple examples down here on how to use these guys so that we are ready for practice problems that we will do tomorrow in class. So let's try this out. Okay, so the first example we're going to use is SF4. So let's go ahead and try to draw this SF4 example. So we have sulfur bonded to 4 fluorines, sulfur tetrafluoride. Now, going to work the Lewis structure, number of valence electrons. Sulfur has 6. Each fluorine is 7, so that's a total of 28. We'll add those 2 together, and we're going to get a 34. So we've used up 2, 4, 6, 8 so far. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have 2 extras. And remember, if we have 2 extras, we put them on the central atom. It's going to be more than an octet. Sulfur can do that because it's a period 3 or greater, uses those unused d orbitals. Basically, what we're being given here is 4 bonding and 1 non-bonding pair. There's our non-bonding pair right there. And so let's kind of scroll up here and see what's going on with a 4 bonding and 1 non-bonding. And there we see it there, 4 and 1. We're going to call this guy a seesaw. That's the name of the molecular geometry. We'll talk more about the bond angles that occur in this guy tomorrow. Okay, on our next one we have IF5. So this is going to be a central iodine, and it's going to have 5 fluorines coming off of it. So I'm going to go 1, 2, 3, 4, and 5. So we have 7 valence electrons on fluorine plus 7 valence electrons on the iodine. So that gives us 7 times 6. We have 42 totals here to deal with, and so we're going to go 2, 4, 6, 8, 10 used for the bonds, 12, 14, 16, 18, 22, 18, 20, 22, 24, 26, 28. Just like that. Believe I still have a couple. I'm going to go ahead and throw them on the bottom down here. Just like that, and so that should constitute 42. Now, central atom, we're looking for bonding versus non-bonding domains. Once again, we have 5 bonding, and we're going to have 1 pair of non-bonding. And so this is going to be a 5 and 1. So we're going to kind of scroll up here and look for a 5 and 1. There we go. There's a 5 and 1 right there. We're going to call this square pyramidal. Square pyramidal. And that's the molecular geometry for that. We'll talk more about the bond angles that occur here and more about what this shape really looks like in a three-dimensional form tomorrow. Your homework tonight was just to take notes, no practice problems.